Actually,
Hi everyone, thank you so much for joining. We'll just wait for some seconds and let more people join in, and then we'll kick off our webinar. Thanks to our attendees and okay, Eric's here now. So, hi everyone, and welcome to our webinar, How to Do Full Text Search with SingleStore. My name is Yukti Divedi, and I will be your moderator today. One of my main jobs here at SingleStore is to organize weekly AI webinars. We organize 2 or 3 webinars per week. Like this week we had 3. So we demonstrate data and AI use cases, different tools and technologies, or like topics that are really trending these days. So yesterday we had a webinar with Rockset customers, and feel free to check it out. And if any of these topics are interesting to you, please feel free to connect with me on LinkedIn to stay on top of the loop. You can also connect with people from SingleStore and just drop in a message to anyone if you're interested about the product. So I'll also like to hear your feedback or ideas on topics that you would like to see in the future sessions. So please feel free to connect with all of us and drop a message to me on LinkedIn or email at us at team@singlestore.com. So can you please go to the next slide, Eric? Speaking of future sessions, we have got several informative new webinar sessions that are coming up that are visible on your screen right now. Just scan the QR code and it will directly take you to the landing pages. On 22nd July, we have SingleStore as the best operational DB for AI. On 24th July, we have built a text to SQL RAG pipeline with SingleStore and Easy Insights. And on 25th, we have how SingleStore monitors tens of thousands of clusters with petabytes of data in real time. So if any of these topics are interesting, please feel free to RSVP right now, and I hope to see you all there. So coming back to today's topic, you're welcome to participate in the discussion throughout the session using the Zoom Q&A button. It is present at the bottom of your console. We have an internal mission statement to try to answer 100% of the audience questions, even if that means following up with people afterwards via email, because sometimes the questions are really specific and they cannot be taken during the webinar. So just make sure that you have logged into Zoom with your actual name and email address, because we will not be taking up any anonymous questions. So Eric, can you please go to the next slide? We love you all to have a dynamic experience during this webinar. So feel free to try out SingleStore notebooks today. Anyone who tries it will be entered for a chance to win either branded new AirPods Pro or Meta's new Ray-Ban LLM smart glasses. It's absolutely the winner's choice. Simply click the link that is present on your screen. I will be putting everything in the chat as well for anyone who joins late or misses it. So just log in. It will just take a few seconds. You might know that SingleStore has had a free trial offer for many years, but just in the past few weeks, we have also announced a new free share tier, which we'll talk about a bit later today. You might have also noticed that we have a new auto RSVP features to our future AI webinars option on our website. So if any of these landing pages you visit, there's now a checkbox to actually auto register, which will add future upcoming Zooms automatically to your calendar, which obviously you don't need to join each webinar live, but this is just an option for those that have requested to automatically receive the video recordings and GitHub links that are useful for the session. So moving on, allow me to introduce our amazing speaker today. Joining us today is Eric Hansen, who is the Director of Product Management here at SingleStore, along with his rich experience in designing and building systems software for database warehousing. He is an expert in memory, column store, and vectorized query execution technology. Eric, I'm so happy to have you as a speaker today. Welcome. The floor is now yours.
hey, Yukti, thank you so much. And welcome, everybody. And it's my pleasure today to talk to you about some exciting new full text search features that we've just introduced in the last few weeks in the 8.7 release of SingleStore. And so for those of you who may be a little bit new to SingleStore, I first wanted to tell you what SingleStore is. So SingleStore is a SQL database with scale out, and we're a multi-model database, meaning we support the relational model with tables and also support things like time series, full text search, vector-based search, JSON or semi-structured data, all in one system. So you can do transactions, analytics, semi-structured data management, search, all in one place. And that's really powerful for developers. It makes their life easy, so you only have to buy and learn one product, and they don't have to move so much data around. So we run in the cloud as a cloud service, and you can also run us self-hosted if you want. And again, we're great at transactions, analytics, and search. A little bit about how we work under the hood can help understand the rest of what I'm going to tell you. So underneath the hood, when you load data into SingleStore or insert data into SingleStore, our default table type is a disk-based column store. But in front of that, we have an in-memory sort of speed layer that can accept newly inserted rows really quickly using an in-memory row store structure. And that's part of your column store tables. So that's an in-memory skip list. And then the data, after it's been in the system for a while, ages into a column store format asynchronously. And within a few minutes of being persisted to disk, it'll be written out to an object store layer for tables that use what was known as unlimited storage. And our systems are clusters or workspaces made up of several nodes. So the front end nodes are called aggregator nodes, and the back end nodes are called leaf nodes. So a table is split up horizontally across multiple leaf nodes. In this little picture right here, you see, these are workspaces with one aggregator and 4 leaf nodes. And users connect to the aggregators, they submit their queries, and the aggregators farm out pieces of the work to these different leaf nodes. So we're extremely scalable. You can scale from anywhere from a single compute node running both the aggregator and the leaf components to arbitrarily big systems that have literally up to a couple hundred nodes. Now, we have customers in production on 2 cores, all the way up to 1 to 2,000 cores for a single system. We scale as small as you want or as big as you want. So today, I'm going to talk about full text search support in SingleStore. And to begin, I want to give you some of the history of our full text search. So SingleStore has had full text search since 2018. We call that full text search version 1 that we introduced in 2018. And it was based on an open source project called SingleStore. And it's compiled and built into the SingleStore database engine. It's very capable for English-based search. It performs well, but that SingleStore project has not been actively enhanced in the last few years. And there's a more modern full text search open source project called JavaLucine that is very popular, and it's continued, the open source community has continued to enhance that, make it better, and brought some very compelling new features. And so just in the last release in 8.7, just a few weeks ago, we introduced a new version of full text search called version 2 that's based on JavaLucine. So it's very similar to the previous version and how you use it. There are some functional differences, but it brings some new things to the table. So why did we update full text search now? Many of our customers asked us to modernize our full text search in various ways. And looking at what's available in JavaLucine, it just made it possible for us to add some significant new benefits. And also, everybody knows that in the last year and a half, generative AI has been extremely popular, and people are really trying to figure out how to do generative AI applications on top of their enterprise data or their database data. And they want to do what's called retrieval augmented generation and be able to find the data they need with both vector-based search and full text search, and feed that into their large language model to do question answering with what's known as RAG, or retrieval augmented generation. So that's made text search even more important because people want to do a great job with RAG. So that's why we updated full text search now. And full text search version 2, based on JavaLucine, brings a bunch of benefits, including, just a modern text search engine. It's the same text engine that's in Elastic and Solr. So Elasticsearch and Solr are popular search systems that are open source. It enables us to do things that we couldn't do before with full text search, including proximity search, which is, finding text where there's certain words within some specified distance of each other. Fuzzy matching, which is like being able to find, misspelled words and that kind of thing. Boosting, where you can give more importance to certain terms. BM25 scoring, which I'll say more about, which is a modern scoring algorithm that's better than the TF IDF model that we previously used, and JSON search as well. So now we allow you to search on JSON documents directly. You don't have to convert your JSON to text and just search that. So there's also some additional benefits of moving to version 2 for us and eventually for our customers, which is that it allows us to introduce customizable tokenizers more easily. And so customizable tokenizers, the tokenizer is the piece of code in a full text system which takes the documents and breaks it up into words, basically, or tokens. And that's going to allow us to do a few things, like a popular kind of search is related to, it's called n-grams. And then also we support English search today, but we want to enable foreign language search. And there's a suite of tokenizers for Java Lucene for all the major foreign languages. So we'll be able to introduce foreign language search in the future. So these things are now on our roadmap in the not too distant future. So what's special about SingleStore and search? We are the only database management system that has all these things. The first is distributed SQL query processing. So I talked about aggregators and leaf nodes and how you can scale to arbitrary size. You can handle any size workload from the smallest to the largest with a single product with SingleStore for both transactional and analytical processing. We support indexed vector search since the 8.5 release at the beginning of 2024. So indexed vector search or approximate nearest neighbor search is very important for doing a great job of semantic search and retrieval augmented generation related to text. And now we have modern full text search with all these things I mentioned, like BM25 scoring, boosting, fuzzy search, proximity search, and JSON search. And this, altogether, this brings together unique capabilities for hybrid search, which is great for just search in modern applications, as well as retrieval augmented generation support. And if you want to learn more about these unique capabilities of SingleStore, check out the new blog that I wrote about SQL full text platform for Gen AI. And there's the URL at the bottom. So the way we implemented support for full text search version 2 is with what we call a co-process architecture. So each machine in SingleStore, each aggregator or leaf node has a process running on it called memsqld, which is the SingleStore service process or daemon. Memsql is our old name before we rebranded to SingleStore. So that's still there in the code. So memsqld is a service process that accepts SQL queries and runs stuff, in native code implemented in C++. Java Lucene, that process is called JLucene, and those two processes now communicate with each other to do full text search. So you send your queries directly to SingleStore, and if there's a full text search operation in your query, it will farm it out to the JLucene process. It's fully distributed, so there's a JLucene running on each leaf node and each aggregator node. So pieces of your query will get farmed out to JLucine, and those two processes communicate via shared memory and Unix sockets. Now, if you happen to be self-hosting and you want to, troubleshoot, you can see, the s2jlucine.jar will be run by the Java. And you can use PS to see all the processes that are running and look for that particular process. And that's the JLucine process. So just a little background about how it works. And then if you want to create a table with a full text search version 2 index, you use this kind of syntax. You say, create table, and then you have your fields. You can create full text search on top of multiple fields, a full text search index on multiple fields. In this case, you've got title and body, two separate fields in the articles table. One's varchar, one's text. So text is like arbitrarily large size text object. Varchars, of course, variable length char up to 200 chars. And you see it says, we're creating this index on both title and body using this full text using version 2 clause. So you can search either title or body or both in your queries. And you can also create a full text search index over JSON. So here we've got title and records are, this is varchar and records is JSON. So suppose we want to create a full text search index on both of those. We do it just like this. So records is JSON. You can create a full text search version 2 index on that. That was not possible before with version 1. So a lot of people want to full text search their JSON directly. So this is going to be really popular. So let's talk about fuzzy search and how to do a full text search query through SQL. So this is the first full text search query you're seeing. So I insert into T the Tempest and then a little JSON document that says author Shakespeare. And then we could have other stuff in this JSON document if you wanted, but this, just for simplicity, I'm just having this really small JSON document that has one property with the author. So the Tempest, written by Shakespeare. The Grapes of Wrath, written by Steinbeck. Okay, so here's a full text search query. So select star from T where, and then we use this match against clause in the where clause. So match table T. This is new, this keyword table in front of the table name. Before you'd say match and some fields against your full text search query string. Now you just say match table name against, and then the full text search query string is in the against clause. And so this query string syntax is the syntax that you get from Java Lucene. So if you want to, we've documented this, but if you want even more examples and super in-depth documentation, if you look at the Java Lucene documentation, you will see, all the details about the kind of syntax you can use in the against clause. And this is a fuzzy search example. This Steinbeck tilde says find everything within one or two characters of edit distance of Steinbeck. So it can find, so in this case, the query has a misspelling. It should be Steinbeck, but someone wrote Steinbeck. So it actually found Steinbeck since we just have to change one letter from an E to an I, and then we find it. So that's an example of fuzzy search. It uses what's known as a Levenstein distance calculation to find stuff within one or two characters of edit distance. And that's insert or transposition of characters. Next, I want to show you how to do proximity search. So I've created this table S, couple rows added, red, green, blue, and red, yellow. Here are some text. So 1, 2, 3, 4 words, and then the word purple. So here's a select star from S, match table S against this full text search string. So this says in field T, find yellow and purple separated by no more than 4 words. So it found red, yellow, here are some text purple, because there's only 4 words between yellow and purple, so it found it. But the next one down at the bottom, we say, we do a proximity search with ~3, and that means find stuff that's no more than 3 words apart. But this is yellow and purple are 4 words apart, so there's no results output. The empty set is output. So it shows you the difference, shows you the meaning of this, that this. So if you want to find words that are pretty close together, but within some specified distance, this is how you do it. The next thing I want to show is boosting. So boosting is a approach where you can modify the scores of your query by giving certain terms higher weight or giving them a boost. So here we're doing match against, red boosted by 2 and yellow boosted by 4. So the default is 1. If you don't use that tilde, that little hat character with a number, it's just everything defaults to boost 1. So looking for red and yellow. So red and yellow both appear in the first one, and only red appears in the second one. So you see it got a pretty high score, a boosted score from that. And then next, suppose we do red and yellow without any boost, you can see the difference. So instead of 0.78, we got 0.26 for the first one. Instead of 0.26, we got 0.13. Next, I want to move on to talk about BM25 scoring. BM25 is also known as best matching, number 25. BM stands for best matching. If you want to see all the details about how it works, you can look at that Wikipedia article about Okapi BM25. And BM25 better accounts for document length and what's known as term frequency saturation than the earlier scoring algorithms that were popular. As I mentioned before, we used TF, IDF, which was term frequency inverse document frequency in the full text search V1, which is a very capable scoring strategy, but it's qualitatively not as good as BM25 based on experience by modern full text search researchers. And so here's an example of what I mean by term frequency saturation. So suppose that you're searching for documents about elephants, and one document has the word elephant mentioned 200 times, and the other has it mentioned 100 times, but they're both like 10 or 20 page documents. Obviously, just because the first one has mentioned elephant 200 times, it's not twice as relevant as the one that mentions elephant 100 times. If you're searching for documents about elephants, I mean, that's so many, the mentions are so many, so numerous that they're both obviously about elephants with high relevance. So what BM25 does is if it sees a term a lot relevant to document length, related to document length, it's not gonna weight it as highly. Like it's not gonna give you a linear increase in score as the number of terms increases. That the increase in score will decay and become less and less significant as there's more and more of them. So here's just an example of how to use it. Note that this is partition scoped. So SingleStore uses a partition storage model where the database is broken into multiple partitions, and they're typically 1, 2, 4, maybe 8 or more partitions per leaf node. And scoring is local to the partition with our BM25 scoring. In the future, we're going to add a scoring model where the BM25 scoring is global across the entire table. For now, it's partition scoped, but it tends to perform very intuitively and work just fine when it's done at the partition level. And this is similar to how things are done by default in Elasticsearch, for example. But some people want global scoring, so we will introduce that in the future. This particular select statement shows us how you can use the BM25 function to get the score weighting for just a specific term. And then you can combine these with a mathematical expression to weight them if you want. So, this particular one gets red and yellow with the BM25 score for each, and then weights the score for the first one, red, 60%, and weights the score for yellow at 40%. And then this is the final output down here. So, you got 0.131 and 0, 0.131, 0.131. And then here's the weighted combination of the two. So that's BM25. So just remember, 200 elephants is not twice as relevant as 100 elephants. That's what BM25 is all about. Another important thing to understand about how our full text search works is search latency, and index latency. So full text indexes are updated in SingleStore asynchronously. So when you add data to a column store table, the new data goes to an in-memory row store segment of that table. And then we asynchronously update the indexes. So as data ages in the row store segment, within a couple of minutes, it will be, or as soon as that row store segment gets full, by some definition of full, we'll write a column store disk-based segment. So when we write the column store disk-based segment, that's when we build the full text search indexes at the time we write that out. So the documents are not searchable until they're flushed to the full text, to the column store segment, and the full text index is built on those segments. Indexes are per segment. A segment is a 1,000,000 row chunk of a column store. Typically, you can control segment size, but that's a typical size. And each partition of a table consists of multiple segments, at least one segment, potentially more. To control flushing and full text index build latency, you can control the flush size maximum, which is called column store flush bytes. This defaults to 32 megabytes. And you can control the flush max latency with internal column store idle flush wait seconds. That's a variable that you can set. It defaults to 125 seconds, so just over 2 minutes. You can, if you want to be able to search documents quickly, like in 5 seconds, you can crank that down to 5 seconds. Optimized table flush versus a manual flush. So if you've just done a big load or big insert and you want to immediately make those documents searchable, you can just run optimized table flush. But you don't need to do that typically because you can just wait for the automatic flush. A little more about troubleshooting. If you might not troubleshoot how much memory is getting used for full text search v2, you can do show status extended like alloc FTS2 service. That's an allocator variable that shows how much memory is getting used for full text search v2, and the way it interacts with the external Java Lucene process. So there's an example of output. Note, if you don't get any output when you do this search, it might be because it's a 0 and not actively being used. If it's 0, the output is suppressed. Further regarding troubleshooting, if you want to see the service status for the full text search service, the external Java Lucene service process, just say show full text service status and you'll get the status, and it looks like that. Additional troubleshooting can be done by looking at the trace logs. If you happen to be self-hosted, you can look at the trace logs directly on the cloud service. We have it available. It's not visible to you, but there's a jlucene 0.log that has it's about the Java, it's logging of status from the Java Lucene service. And then jlucene.out contains some redirections from that process. And it has things like the command line used to start the service and some operating system errors or uncaught exceptions and stack traces. So if you want to try out full text search v2, I recommend just try our cloud service. It just works. You don't have to set it up at all. It's automatically set up. If you want to try it self-hosted, you can do that. All you need to do is you first have to install the JDK, the Java Development Kit, and you must be using the Java Runtime Environment number 21 or JRE 21. And so these commands, you can use SDB admin. So we have this set of tools called Toolbox that consists of SDB admin and SDB deploy. And in order to run the full text search, you need to install the JRE 21 on all the nodes in your system at the same spot, the same location, and then use SDB admin update config to set the Java home and Java path variables you see there in purple to the location where your Java home and your Java path are. And I just gave an example of the way it is on my installation, but yours may be different. So put in the right value for the path there, and run the command just like this with the yes, double dash yes to make it interactive and not wait for any prompts, and then just restart all the nodes in your system, and then Java will be accessible and you'll be able to use full text search v2. You have to verify that all the Java files are readable to all users. Or really just the memsql daemon user, but just make them readable to all users. You can use chmod 755 or something similar to make it readable to everybody, so the memsql service process can read it as well. So with that, I want to move on and give a demo. Now might be a good time. Are there any questions that have been coming in that aren't handled? Anybody that you want to pass to me? Any of the other moderators have a question for me before I go on?
We actually don't have questions that are unanswered. So if you would like to reiterate on this one question from Sachin Mehta, they say that what algorithm is used for proximity search? Any specific distance-based ones would be interesting to learn.
Yeah, I don't really know the answer to that, what we use for proximity search. I mean, I know what we use for fuzzy search, but proximity search it's pretty simple algorithm, really, because we know where each term is, and what term number it is within the document. We can just subtract to find the distance. So it's pretty straightforward algorithm, I think.
Right. So I think we can move on to the demo. To everyone that's attending, please feel free to keep the questions coming in. We will take them up before the end of the session. We have an amazing panel with us today. So please feel free to either ask them right now, or you can drop an email at team@singlestore.com. The code to the demo is also in the chat. I have put it there. So that link seemed to be private. I had some questions regarding that. So I've also put in the file for everyone to access. So please just go right ahead and follow along with Eric and you can just have a hands-on experience with SingleStore. All right, Eric, you can just start.
Thank you. Yeah, and so our panel consists of one of our product managers who handles storage and query work in SingleStore, as well as our writer for full text search and the chief developer and technical lead for full text search. So you're in good hands. If you want to ask questions in the chat, please just fire away. We'll be happy to answer all your questions. So I wanted to demo using full text search, live for you on a real set of documents, make it a little more exciting. Those toy examples I showed you before are great because they're small and compact, but let's try it on a real data set. So I want to search video game article paragraphs using full text search v2. So we created a small or sort of medium-sized set of document data where we scraped Wikipedia for all the articles about video games, and we created a row per paragraph from these articles. And we also got vectors from OpenAI for each of these paragraphs, so we can do semantic search with vector-based search on the same information. So I'm going to show you several full text searched examples with full text search v2, and then just then do a hybrid search example. So here's some of the characters we'll talk about: Mario, Wario, and Princess Peach. So by the way, whoops, hang on. Okay, now I'm going to switch screens to our customer portal. Can everybody see this? Now it should be showing the customer portal.
Yes, it's visible.
Okay. All right, so I wanted to demo this video game search with you, and here's the table. The table is called Vex, but it's got a URL, which is the Wikipedia article URL where the paragraph came from, and then the text of a full paragraph from the article, and then a vector for that paragraph that we got from OpenAI, and from the ADA 002 model, 1,536 elements long. And then we said, I want to do full text using version 2 on the paragraph text itself. So this clause right here says, build a full text search index on that paragraph. And I'm sharding on the ID numbers. ID is a big int. So every vector, every row has a unique identifier that's an integer. And so this evenly spreads the data out across all the nodes. So I originally loaded this. It's already loaded, so I'm not going to run this again, but I loaded this using this pipeline. This file is readable by anybody in the world. It's in US West 1 and doesn't need any credentials because it's got no, it's readable to everybody. And so I just created this pipeline, and I started the pipeline in the foreground to load everything, and that loaded in just a very short time, just like a few seconds. It loaded all of this information. And then I said, optimize table flush to make sure it's all out in a column store format. And also to make sure that all the vector indexes got created, as well as the full text search indexes. So now this is a narrow phrase query. So I want to find everything that has in paragraph the phrase image metrics. So those words next to each other. All right, so let me run this. So only one of the 40,000 paragraphs has that phrase in it, image metrics. So inside, so I just hover over that paragraph output, and that's the full text of the paragraph. So in there, someplace is the phrase image metrics. You can see it on like the 6th line, I think, there on the right. So now let's show you how you can search for terms in named fields. So there's only one field indexed here, so but I can search for the word image in paragraphs and the word euphoria in paragraphs and see what I get. So it actually got the same document as before, and I did that by design. It's just this one paragraph contains image and euphoria. They're not right next to each other because it's not a phrase search. It's just it's a term search for those terms. They can be anywhere in the document. All right, so next, let's look at ranked output. So I was just here using the match against and the where clause. Now I want to use match against in the where clause to focus in on just finding documents about Princess Peach. But I also want to find their scores and output that in the select list. So you can use match against, if you use the same exact match against clause with the same exact query in both the where clause and the select list, that will give us, it will allow you to find stuff that has a score 0 or higher. By the where clause, it'll be true if the score is higher than 0. So it has to match something. And then the output, it will give you the score that was found. So the actual numeric score. So again, in the where clause, it's just true or false, but score greater than 0 means true. So let's do this. And I'm just going to limit to 5 rows of output in ranked order. So here you see that I've got 5 rows of output. And so Princess Peach is a character in the Mario game franchise. So like here, if you look at Paper Mario, okay, see if I pop, I know it's kind of small, but you see it mentions Princess Peach, read that text. It mentions Princess Peach several times. I see at least 4. And so that's why it's ranked so high. It's got a score of 7.9. It's ranked high because Princess Peach occurred many times in that short document. And that boosted it up. So one thing to notice is that scores in full text search v2 can be any positive number. So they can be any number that's greater than 0. They won't be negative, but they can be greater than 1. So in our previous full text search system, it was very unusual. I don't think you could get a number greater than 1. I would think they were weighted in the range 0 to 1, or at least I never saw one that was greater than 1. So, but scores greater than 1 with J-leucine happen all the time. So if you want to normalize the scores into a certain range, you may need to take that in consideration. I'll talk more about that. So let's get the top match. Now here's an example about, suppose we want just the top match for the game description that's most about Wario. You can just do a limit 1. And so this game is about Wario. Okay, so you read that, you can talk about Wario. You can hear about Wario. So now let's look at the next one. I suppose I want to make it easier to write this query. Unfortunately, I had to redundantly specify this paragraph Wario, both in the select list and in the from clause and then the where clause. To make things simpler and less redundant, I can use a session variable. So there's a session variable TQ that stands for my text query. And then you see I use TQ in both of the match against clauses. So I only have to write it down once. And so that gives us the same result that we got before. Now here's a good one that, this is an AND query this is interesting because if you're a Mario and a Wario game aficionado, you know that garlic gives Wario special powers. So if he eats the garlic, then he gets superpowers. So let's find documents that have both Wario and garlic to read about that. So here, there's 3 documents that talk about his ability to get magical power by eating garlic. Next, suppose there's a kind of games called open world games where there's not a fixed number of levels. You just kind of roam around in a world that has no fixed boundaries or levels. And if you're a game aficionado and you're studying up on, what are some cool open world games, you might want to search for that. So now I needed to use a limit clause here because there's so many paragraphs that mention open world. There's like, almost 100. So this gives me the top 10 open world matches. So next, suppose I want to do hybrid search where I do vector search combined with full text search. So I created a helper function here, which I won't go through the details of it, but it's like a heuristic function that normalizes scores that are greater than 1 into a 0 to 1 range. So it helps me do that with some other logic that I have in a query. So suppose I want to get information about Mario Kart, and I want to do a vector-based semantic search combined with full text search. So I've mentioned the term semantic search several times, but what semantic search means is you search based on meaning, not just keywords. So full text search is super powerful, but it's limited in that it doesn't really understand the text. It knows about the words that you asked about. So semantic search, if you get a vector for a document that contains female monarch and another and a vector for a query that contains the word queen. So queen and female monarch are the same thing. So a vector similarity score between those two will be extremely high. And that is one of the powers of vector-based search, is that you can search based on meaning, not just based on keywords. So because of the advent of large language models and the power that they have for generative AI, the full text search sort of market and technology space is under kind of a dramatic upheaval right now, because people know they need semantic search, that full text search is not good enough anymore. They want to reach for the stars and be able to search based on meaning, not just based on keywords, because it's just more powerful. Nevertheless, full text search gives you a lot of control, precise control, and does certain things better than semantic search. So it's natural to want to combine them, and that's what I call hybrid search. So here we're going to search for articles about Mario Kart. So we got the Mario Kart contains a vector for Mario, a paragraph that's about it's the first paragraph of the Mario Kart article, so it's all about Mario Kart. And then we have the keywords Mario Kart. So this is a hybrid search query that uses common table expressions. The first one here is the full text search one. So I'm going to get the top 200 matches about Mario Kart based on full text search with version 2. And then this particular common table expression is doing a dot product of the vectors with the vector for Mario Kart. So I'm going to get the top 200 here. And then I'm normalizing the scores for full text with this simple expression, that does norm TS. And that will normalize my scores to a 0-1 range. So when I combine the vector scores with the full text scores, I get something that is sort of intuitive, and that I don't the full text scores are not overweighted, because the vector scores are in the 0 to 1 range. So now I'm going to run this whole thing. Let's see if it runs. Oops. Okay. So that whole query ran, and it ran in 39 milliseconds. So that's pretty quick. It's able to do that because it's using both a approximate nearest neighbor index to do the vector search, and it's using the full text index to do the full text search. And then it's combining the scores. And you can see that this is the vector score, and this is the normalized full text score. And it's pretty cool to see that the vector scores and the full text scores are not in the same order. And then I'm combining them with a weighted sum, giving 70% weight to the vector score and 30% weight to the full text score. And you see, I divided by the norm value. I'm doing a cross, full text search rows cross join with a normalized text score, and then doing a full outer join on that with the vector score common table expression. And so even if something was like super high with a vector score, but it didn't contain any of the keywords we're looking for, we can still get it with the output of this query because we're doing an outer join. Okay. And so here's the top 5. And so that's how to do hybrid search with SingleStore, which is a great way to get information to feed into retrieval augmented generation, or just to get high quality search results that have both meaning and keywords taken into consideration. So with that, I would love to invite you to join us for other webinars. As we discussed at the beginning, we have several webinars coming up, and a lot of them are about AI and retrieval augmented generation and doing vector search with SingleStore, using SingleStore's vector search to enable AI enriched database applications. So stay tuned for those. And again, you can try to win the prize today. Go enroll in the raffle there. Look at that URL. And I want to thank you all, and we can take some more questions. I know that our panel of experts has been answering a bunch of questions live, but if you would like, I'll be happy to take more questions right now.
I just have one request, Eric. Can you please update the link to have public visibility, like the one you shared with me earlier?
Which one is that? You mean the full
The
text
one, the
document?
SQL script, the SQL script you shared with me.
Okay, sure.
Yeah. So everyone that had questions regarding the SQL script not being visible, we are addressing that. And I hope you are also able to access the file that I have put in the chat. And just keep the questions coming in. We have an amazing panel of experts that is expert in data. So please, we actually have one question from Anandmoy Sarkar. They are saying like full text search version 2 supports full text indices on JSON columns. Does full text search perform as good as full text search on normal text field? Presently, we are creating persistent text columns to convert JSON columns so that full text indices can be built on top of the persistent column loops. Can you suggest any improvements, or if you can just reiterate on that?
Yeah, you don't have to do that anymore. You can just put an index directly on the JSON field, and it'll perform on par with whether it was just a text field.
And we also have some good feedback from Klaus and Robert that thanks for sharing. What a cool session. So
Oh, thank you so much.
there as well. So I also have one question. So this was a very amazing session. So you explained very well that how SingleStore's full text search has been able to efficiently handle large scale data. So do we have any like customer stories that we can actually share? Like, is there someone that's actually using this feature currently?
So this is a brand new feature, but it just shipped just a few weeks ago, and a bunch of customers are using it. It's still single digits. It's like mid to high single digits are using it. And, lots of people were already using full text search V1. And of course, they're not going to migrate their applications overnight. The syntax is different for the match against clause, a little bit different, and the way you create your index is different. So it's going to be like a port. It's not going to just be a direct replacement, but we expect that a lot of our customers using full text search V1 will convert to full text search V2 as they want to enhance their apps. Full text search V1, we're going to keep supporting it. Don't worry, we're not going to take it away. It is deprecated, however, in that we really advise people to use full text search V2 for new application development. We're not going to be enhancing full text search V1 anymore, but rest assured you can keep using it if you want.
That sounds really good. So I think it's more like feedback that, hey, thank you for the session. We don't really have more questions, and thanks for answering my question as well. And the panel has done a great job addressing the other questions. So I think we can conclude with the announcement that everyone's been waiting. I want to announce the raffle winner for today.
Ooh.
Yeah. So so we do a random draw every time within the attendees. So the announcement that everyone's been waiting for, today's raffle winner goes to Vasiolis Fasolas. That he's the head of engineering at Heat Geeks. It's a startup, and it deals with some AI solutions and building data warehouses for I think it's Gen AI grade data warehouses, something like that. I'm not able to find a lot of information exactly what these guys are doing, but congratulations and thanks for joining, sir. If that is not you, please feel free to sign up with the link that Eric shared earlier, and please feel free to use the code that was provided earlier that has been made public now. We will follow up with the recording in our follow-up emails, and I hope to see you all in our next sessions. Thank you so much to the panel. Thank you, Eric, for joining. Thanks to all the attendees, and I hope you all have a great rest of the day. Take care, everyone.
Thank you so much. Thanks for joining, everybody.
Yeah. All right. Bye-bye.